Okay, so just going to review what we did last session. So last session we looked at Bose notation, labeling spaces. And we said that we labeled the spaces between the forces and the members. And that it might be helpful at first to draw a circle around that, just so we can visualize what's going on a bit better, but that once we get confident we don't have to bother with the circle. So usually I would recommend we start labeling between the reaction forces, work our way around clockwise, and then fill in the spaces in the frame. Okay, so we've got a couple of examples there, and here we've got one where we've not put the circle around. But we start between the reaction forces and then label each space between. And it doesn't matter if you've got A, B, C, D, E, F, G, H, I, or you do it like I've done it, as long as you then use this information to inform the way you go about the next step. Okay? And then went through the next step without making any use of the Bose notation. But, I just thought we could have a look at the next step first. So now the next question then is, how do we apply the Bose notation to this? And the next step was that we drew the forces that we knew to scale. There we are, drawing it to scale. Next force starts where the other one stops. And we pick an origin point, doesn't matter where the origin point is. And then we draw lines from the start and the ends of the vectors, start and the ends of the vectors, to our origin point. Okay. Then we take that orange line, we take a parallel line and we run it through that point there until it hits a construction line that's sort of the extension of the force. And then we move down to our next line, the green line, and we move and we draw a parallel line to that from that point to the next extension line of force. And we can see that going on here as well. So we orange line parallel from the start to the first line of force, the green line parallel from the second line of force to the from there to the second line of force, and then our bluish line takes us to the end. Then we draw a line from the end back to the start, and that's our purple line here and our purple line here. And we draw a line parallel to that line through our origin, which you can see here and here. And then where that line, draw that line through our origin, and where that line crosses marks our reaction forces. So the bottom section is reaction force 2, that's reaction force 2, reaction force 2, and the top section is reaction force 1. Reaction force 1. Well, how do we know that? Well, this is where the Bose notation comes in. This is where the Bose notation comes in. So we've drawn our vector, okay, and over here on our space diagram, this vector could be said to be BC, okay, because it separates spaces B and C. Yeah, this member here, there's this diagonal here, separates spaces C and D, so it could be said to be member CD. Yeah, this member could be member BD because it separates those two spaces. This force here, this force here would be CA if we're working our way around clockwise because it separates space C and A. So we label the lines by the spaces that they separate. Okay, that takes a little bit of getting your head around. So this line here is BC. So what we do with that is in lowercase, if we're going around clockwise, we say we start at B and we go to C. So we start at B, oopsie daisy. We start at B and we go to C. And it becomes important that we keep consistency about which direction we go around when we're naming these, and that just use lowercase for clarity. So what we've found when this purple line crosses is we've found point A in this case, or whatever letter you have put between your reaction forces. Okay, if you've put a smiley emoji between your reaction forces, we've just found the smiley emoji point. Okay, so let's just label that up as point A. So we found point A. So now if we look at this with fresh eyes, if we go from, we said this vector separated spaces C and A as we go around clockwise. So from C to A is reaction force 2. So we can get a ruler and we can measure that distance, and that tells us the size of the reaction force. Okay. Now, obviously, just looking at this very simple example here, it's 10 newtons, it's symmetrical, so it's going to be 5 newtons either side. And we can see that this purple line intersects our 10 newton vector at the halfway point. So we've got 5 and 5. Okay. Yeah. So, but yeah, from C to A, C to A. From A to B, A to B is our reaction force 1. And that's a start of how we use our Bose notation. Let's see how that pans easy for me to say. Let's see how that pans out over here. So we've got our 5 newtons, which is B to C. Okay, so let's just copy that B there. Let's put that there, B, and let's copy our C there. There we go, B to C to the end there, and then we've got C to D, which is our 12 newton force, separate spaces C and D. So we've got D at the bottom. So let's just copy that and edit that. So you notice I'm using all lowercase on my force diagram. This is a funicular diagram. Actually, this is called a funicular diagram. Okay, and then we've taken this line and we've made a line parallel to that through our origin point, and we've said that where this cuts our 2 vectors is point A. So let's just move that across, point A. So let's have a look. If we go from D to A, which line are we talking about? D to A, reaction force 2. A to B, A to B, reaction force 1. So we can measure those distances. Yeah, and we see that DA is more, which is what we'd expect because we've got a greater load at that end of the bridge, that end of the structure, and we've got a smaller load at this end of the structure, so we'd expect the reaction force here to be less. Okay, right, very good. Okay, so we're just going to pause there for a moment, and in the next video we'll take the next steps on this, where we find out what the forces are in each of these members and whether it's in compression or whether it's in tension. Thank you.